Lumen point. Let's begin the breakdown.
All right, let's just jump right in. We're about to tackle what might be the single biggest, most profound problem in all of physics. What exactly are space and time? Because it turns out the very stage our universe is built on, well, it might not be real in the way we think it is. Everything starts with this ridiculously tiny number. This is the Planck length, and I mean, to put that in perspective, it's a trillion times smaller than an atom. It's pretty much the smallest possible length that has any meaning. And it's exactly where our understanding of reality just completely shatters. You see, when we zoom down to this impossibly small level, our best theories just stop working. They predict that the very fabric of reality, space-time itself, dissolves into total chaos. It's basically a giant warning sign from the universe telling us that our two greatest theories are missing something huge. To really get why, we need to build up our picture of space-time. And for that, we have to start with the man himself, Albert Einstein, who completely changed the game. You know, for centuries, people like Descartes and Newton thought of space and time as two totally separate things. Space was just this rigid, absolute grid, and time just ticked along unchanging. But Einstein's big idea was that, no, they're actually woven together into one single, four-dimensional fabric. How you move through space directly affects how you experience time. They're locked together in this thing we call space-time. So, how do physicists actually picture this fabric? Well, they use a mathematical tool called a manifold. And here's a cool way to think about it. Imagine a tiny little ant walking on the surface of a globe. To that ant, its immediate surroundings look perfectly flat, right? But if we zoom out, we can see that all those little flat patches are actually stitched together to create one giant curved ball. That's kind of like space-time. And this is the absolute genius of general relativity. Gravity isn't some invisible force pulling things. No! It's just what we feel when we move through curved space-time. Big objects, like the sun, literally bend and warp the fabric of space-time around them. So the Earth isn't being pulled by the sun, it's just following a straight path through a universe that's been curved by the sun's mass. But as beautiful as this theory is, it has an Achilles heel. In really extreme places, like the very center of a black hole, matter gets so dense that space-time is forced to curve infinitely. And in physics, whenever you get an answer of infinity, that's a huge red flag. It's your math screaming at you that the theory has just broken. So that's one pillar of modern physics. Let's turn to the other one, which paints a totally different and, frankly, much weirder picture. Welcome to the quantum realm. Down here, at the scale of the very small, all the rules change. Certainty just goes right out the window. A particle doesn't have one single location. It exists in a cloud of possibilities, a wave of probability. And get this, for that particle to travel from point A to point B, it literally takes every single possible path, all at the same time. And then you have entanglement, what Einstein famously called spooky action at a distance. You can link two particles so that they share a single existence. Then, no matter how far apart they are, across the room or across the galaxy, if you measure one, you instantly know the state of the other. It's a connection that seems to completely ignore the space between. Okay, so we have general relativity for the big stuff and quantum mechanics for the small stuff. Both are incredibly successful. The problem? When you try to make them talk to each other, they speak completely different languages. Our understanding of the universe is fundamentally divided. So what happens if you try to apply those weird quantum rules to space-time itself? Well, you get a disaster. That smooth, elegant fabric from Einstein's theory just shreds itself into a chaotic, bubbling mess called quantum foam, where the very idea of a specific location or distance completely breaks down. I mean, just look at the contrast. General relativity gives us a smooth, continuous, dynamic stage where gravity is the geometry. Quantum mechanics, on the other hand, gives us a world of probabilities and discrete particles playing out on a fixed, rigid background. They are just fundamentally incompatible views of reality. So how in the world do we fix this? Well, the first big clue, the first hint of a deeper reality, came from the most mysterious objects we know of: black holes. Back in the 1970s, physicists like Jacob Bekenstein and Stephen Hawking figured out that black holes have entropy. Now, entropy is basically just a measure of hidden information. It's a count of all the microscopic ways you can arrange the guts of a system. But wait, if a black hole has information content, that means it must be made of something, some kind of fundamental atoms of spacetime. But here's where it gets really, really weird. For literally any other object in the universe, the amount of information it can hold is proportional to its volume, right? Makes sense. But for a black hole, the information is proportional to its two-dimensional surface area. It's as if everything that ever fell into that three-dimensional hole is somehow stored on its two-dimensional boundary. This discovery led to an absolutely mind-blowing question. If a black hole can encode its 3D reality on a 2D surface, could our entire universe be doing the same thing? Is it possible that everything we see and experience in 3D is just a projection from a flat 2D boundary somewhere far away? This wild idea is called the holographic principle, and it flips the whole problem on its head. It suggests that space-time isn't the fundamental thing we thought it was. It's something that emerges from a deeper level of reality. So the holographic principle is exactly what it sounds like. The idea is that our entire universe, 3 dimensions of space, 1 of time, gravity, all of it, is really just a complex hologram. The real physics is happening on some lower dimensional flat surface, and what we experience is the projection. Now, this isn't just some sci-fi fantasy. There's some seriously powerful math to back it up. It's called the ADS/CFT correspondence, and you can think of it like a perfect dictionary. On one side of the dictionary, you have a simple flat world with quantum mechanics but no gravity. On the other side, you have a complex curved universe with gravity, a bit like ours. And the math shows they're exactly the same thing, just 2 different ways of describing the same reality. And the most amazing translation in this dictionary, a pair of entangled particles on the flat boundary is mathematically equivalent to a wormhole, a tunnel through space-time in the 3D universe. And that leads to a conclusion that is just staggering. That spooky quantum entanglement isn't just some weird thing happening inside of space-time. It seems that entanglement is the very thread that's weaving the fabric of space-time itself. The geometry of our world is literally being built out of these quantum connections. I mean, just let that sink in for a second. We've been thinking about this completely backwards. We thought entanglement was a weird feature of our universe. But what if the universe itself, the space, the distance, the geometry, is an emergent feature of entanglement? Okay, now we have to be honest here. This ADS/CFT thing is what physicists call a toy model. The universe it describes isn't exactly like ours. It has a different overall shape. So while it's a massive breakthrough that proves the holographic idea can work, it's not the final answer. The grand challenge now is to figure out how to apply this principle to our actual universe. And that leaves us with this incredible final question. If space and time aren't fundamental building blocks of reality, if they're just an illusion, a hologram, then what is? What is the true fundamental nature of reality made of? Answering that is without a doubt the greatest quest in modern science.
Fuel your curiosity. Subscribe for the explanation. Stay for the knowledge.